Hi guys, welcome back to Algebra 2. Hope you're doing well. Today what we're going to do is relate what we talked about with graphing absolute value functions with what we are talking about solving absolute value equations. So I know that the general reaction when you hear graphing is, ugh, I don't want to do that. And one of my goals this year for Algebra 2 is to convince you that you actually love graphs. Hear me out. I know that you don't like making graphs by hand. That is not enjoyable. I don't even like doing that. However, using graphs once you have them is fabulous. So that's my goal, to convince you of that this year. So today will be one step in that process where I think you'll start to see it. So what I'm going to do is I'm going to go through the examples that we talked about yesterday in the lesson, and I'm going to show you how you can use the graph to verify those solutions that we found algebraically. So we can solve things algebraically with algebra. That's what we did yesterday. We can solve things graphically by using the graph. So that's what I'm going to show you now so you can connect those two. So the first equation that we had yesterday was the absolute value of x equals 7. We were trying to solve that equation. So when we had graphed absolute value functions a couple of days ago, we had things that looked like this, like y equals the absolute value of x. So we would be able to graph something like that. Since I have the equals 7 part on the back of this equation, would it be okay with you if I took this equals y part and flipped it over here to the back, just so it looks similar? I'm going to do that, I think. So let me call these the related graphs. So we could graph the function, the absolute value of x equals y. That equals y can go on the front end or the back end. It doesn't matter. And we want to know where that y value equals 7. So our second equation is going to be, I want that y value to equal 7. So let me show you how that's going to look on graphing. So you're going to use Desmos for this. So I'm going to graph y equals the absolute value. Now, the absolute value bars are right above enter on my keyboard at least, so I hope yours are there too. So I think I have to hold shift. Yep, got to hold shift down to get to them. So absolute value of x, and then I'm going to close that. So you see that V pattern that we talked about. So we said that that's the family of functions. Whenever you see absolute value, you're going to see a V somewhere. So that's showing y equals absolute value of x. Now let me go down to the next line on Desmos, and we want that y value to equal 7. So this green line across is showing us where the y value equals 7. So if you look, these two things cross. The red function and the green function cross at 2 points. This one is located at 7, 7. So remember, when you see an ordered pair, this is an x and this is a y. So one answer is x equals 7, and then our other solution is over here. This is an x, this is a y. So the y equals 7 when x equals -7 as well. And if you look at our notes from yesterday, we had those two solutions. Those were the two solutions that we found. So that's good. Our graph verifies those two solutions. Those are the two places on this V where the y value equals 7. I could go to other places on the function, but I wouldn't have a y value of 7. If I hold down my mouse, you see how it's telling me where I'm at? None of these points, sorry, it's moving really fast. None of those points have a y value of 7, except for these two black dots. So those are my two solutions. Okay, so here is our second example that we looked at yesterday that we are going to verify graphically today. So we have the absolute value of 5x plus 3 equals 12. And I know we already know what the solutions are algebraically. We just want to verify them with the picture and see if it matches. So we could graph y equals the absolute value of 5x plus 3. And we want to know when that comes out to be a 12. So This could be a function, and this could be a function, and we want them to match. That's basically what we're saying here. So I'm going to type this into Desmos. Y equals absolute value, remember it's there above your enter sign, 5x plus 3, and close my absolute value sign. And I want to know when that comes out to be 12. So I want to know when that value equals y equals 12. Okay, so I have a blue line and a purple line here, and I can see that they are crossing at these two spots. So if I look here, when x equals 1.8, we'll get that output of 12. And then the other solution is over here. When x equals -3, we get that output of 12. And that's what this equation was trying to say. It said, I want to know when this comes out to equal 12. So we have our two solutions. They verify graphically with what we found algebraically yesterday. So that's good. So we can have two solutions to this. That's possible. Let's try another one. Actually, I changed my mind. Before we try another one, let's make some steps in our notes for how to verify these graphically. So, solving absolute value. Equations by graphing. So the first step you want to do is graph y equals the left side of your equation. And then you want to graph y equals the right side of your equation. And then you want to look for the intersection points. And you want the x value, x equals whatever, because these equations that we're solving have x as our variable. So x is what we're searching for to solve the equation. So you find the x coordinates there, and those are your solutions. They should verify graphically as well as algebraically. All right, so here is our third example that we did yesterday in our notes. So we already know algebraically what the solutions are, so we just want to verify that graphically. So let's take the left side of this equation and turn it into a function. Y equals the absolute value of x minus 5 plus 4. And then we'll also take the right side and set it equal to y. We want that answer to come out to be 7. So let's graph this on Desmos. So y equals the absolute value of x minus 5. Close that absolute value, and then we have to add 4. That's still on the left side of our equation. Oh, before we go on, let me remind you of how this connects to your transformations that we've been talking about. If you look at this, can you tell that this 5 would be an h value and this 4 would be a k value? H controls shifts left to right. So my vertex, if it was just y equals absolute value of x, would have been down here at the origin, but it has shifted 5 spaces right. 1, 2, 3, 4, 5. Remember that minus sign is part of the setup. It's not part of the h. The h is just what follows the minus sign. In this case, that's a positive 5, which is why I'm moving this way. So 1, 2, 3, 4, 5. And then the k value on the end there is a positive 4. So I go 1, 2, 3, 4. And it maintains the same steepness because there is no a value except for 1. On this, it'd be an understood coefficient of 1. So anyway, just a reminder on that. It's my second equation, y equals 7. Y equals 7 is what we're graphing there. Yep, that looks right. So I have 2 points of intersection here. So one answer is where my x value equals 8, and the other solution is over here where the x value equals 2. So we have two solutions to that. All right, so we're ready for our fourth example from yesterday, where we looked at -2 times the absolute value of x plus 1 equals 12, and something weird happened when we solved that. Do you remember what weird thing it was? If not, look back a day in your notes, look at it and see. It has to do with the fact that we don't talk about distances as negatives. Do you remember that? Okay, so let's see what this looks like if we graph it. So I'm going to take y equals the left side of my equation. And then I'm going to also graph y equals the right side of my equation. So I'm going to come over here. Y equals -2 times the absolute value of x plus 1. X plus 1. Close the absolute value. So there's that one. Let me move that up so you can see it a little bit better. And then our second graph is going to be y equals 12 because I want to know where that value equals 12. Okay, so let me zoom out so you can see this. Okay, so we have this blue line up here where y equals 12, and then we have this b from the absolute value function, and it's down here. And notice its end behavior is it's going down. Okay, so it's going to keep going down like that. So is this blue line ever going to cross this black V shape that we have? Nope. So do you remember yesterday that our solution was no solution on that? Because this isn't going to happen. You're never going to get a y value of 12 on a function that's starting with its highest point here at 0 and then going down from there. It doesn't make sense graphically, and that's why we got no solution algebraically as well. Okay, I want to talk about one last thing that I mentioned at the end of yesterday's video. We said, okay, so we've had problems that have two solutions, equations that give us two solutions, and we've seen an equation that gives us no solutions. Is it possible to get anything else with these, do you think? When you have an absolute value, it's going to make some kind of v and equals like some value. So I want to have you graph this one. So go ahead and pull up Desmos and you graph that. If you need help coming up with your related graphs, it will be y equals the absolute value of x plus 1 plus 2. So I'm taking the left side of the equals first, and then I'm going to take the right side of the equals second. So let's see what this will look like. Y equals absolute value of x plus 1 plus 2. Plus 2. And then our second one is going to be y equals 2. Okay, so if you look at this v that's in green, and this blue line, horizontal line that's in blue or purple, whatever, they are only meeting right here at the vertex of the absolute value function. So the only solution that we have to this equation is x equals -1. Now I wonder why that happened algebraically. Let's take a second and look at this algebraically as well. So if I was going to solve this algebraically, I have x plus 1 in absolute value plus 2 equals 2. And we talked yesterday about how you want to have the absolute value by itself on one side of the equation. So this plus 2, I got to get rid of that. So I'm going to subtract 2 and do that fairly on both sides of my equation. So I'll have the absolute value of x plus 1 equals 0. And remember, we've talked about that absolute value means the distance from 0. So this is saying I have some stuff that its distance from 0 is 0. Well, Where do you have to be standing on the number line if your distance from 0 is 0? You got to be standing right there at the origin. That's the only place. So x plus 1 would have to equal 0, which means if I subtract 1 on both sides, you get x equals negative 1. So that's why algebraically this only has one solution, because if your distance is equal to 0, you don't really need to talk about a positive 0 and a negative 0, because it's the same thing. Okay, well, I think that's everything. So remember that Jesus loves you, and so do I, so do your math.